Hello and welcome to this video. Today we'll take a look at creating a subsurface scattering shader here in Cocos Creator. Before we begin, let's first take a look at the different features this shader offers. We created this shader based on the standard PBR shader in Cocos Creator, so you will still be able to use all the standard PBR's characteristics and features. On top of that, we have one scattering pass using a thickness map. As you can see, there's light coming up from under his skin, and if we turn the value really up, it looks as if there's a nuclear explosion in his head. We also have a diffuse profile feature. Now, without going into the technical details at this point, this primarily changes the scattering color. And finally, we have a Fresnel reflectance feature that helps us control the roughness value a little bit better. In Cocos Creator, shaders are stored in a .effect file. And when you create a new material, you need to pick which .effect or which shader to use. So what exactly is a Cocos effect file? It is basically a document combining your vertex shader, your fragment shader, your custom parameters in one place. Using the PBR standard shader as an example, here is a quick guide for you to get started. All of your vertex shader code should be enclosed in tag cc program standard vs. You can use standard GLSL as well as access Cocos built-in parameters. All of your fragment shader code should be enclosed in cc program standard fs. Your custom parameters should be first declared under Properties in the header. It will make it accessible in the editor. Of course, you need to correspond your custom parameters with a uniform, which is declared in tag cc program shared UBOs. These uniforms can be accessed from both the vertex and fragment shader. You can also declare your custom functions. Just remember to keep them in either the vertex or the fragment shader. So what is subsurface scattering and what exactly are we aiming to create here? We can take reference from photography, and the first thing you'll notice in this example is that his ears are apparently red. And the red color seems to be particularly concentrated at the hard edges on the frame of the ear. Also take a look at the part between the darker and the brighter sections of the nose. You will see there's apparently a belt of red color. In this example, you will see the same red belt, and since her nose is not so sharp, the belt seems to be wider. In this example, the red color seems to be more concentrated on the tip of her nose. Now here, again, pay attention to the part between the darker and the brighter side of his face. Again, you can see a pinkish colored belt in between them. And you can see the same belt on the hard edges of his nose. So why is this happening? Where do these red colors come from? We know that when light is casted into a substance, some of it will be absorbed, others will be refracted multiple times within the substance, and eventually a portion of them will be refracted back out of the substance. And this is why we are able to see the color of the substance. Now you'll notice that these lights that came out of the substance, sometimes we call them diffuse reflectance, they came out of the substance a bit further away from the incident point where the light originally came in. For most materials, this gap is very small and we can pretend they don't exist, and the diffuse reflectance came exactly at the incident point. And this is the case for most diffuse shaders. For some materials, this gap is too big to ignore, and it will create a translucent effect on the material, giving the indication that there is light emanating from within the material. This is the case for many organic materials such as human skin and leaves, and also for rubber, wax, certain crystals like jade. Throughout the history of computer graphics, there has been many attempts to create the subsurface scattering effect. One of the earliest examples is from the movie The Matrix, where they discovered they can simply overlay the diffuse map with a layer of blurred diffuse color to simulate light diffusing under human skin. And to create the color variations, games such as Half-Life 2 deployed the wrap lighting technique. Simply put, this is the technique to use the dot product of the light direction and the surface normal to create a mask to overlay the red color. Most of these techniques, including some of the more advanced modern ones, can only produce an approximate of the subsurface scattering effect compared to what we see in the real world. To create a physically accurate representation would obviously require a lot more processing power and is not efficient for real-time rendering at all. So keep in mind that our goal is to create an acceptable representation of the effect, and we're not running a physical simulation to get perfectly accurate result. So here is the checklist for what we're going to create today. We're going to need a blur to simulate light diffusing under skin. We need a thickness map and a curvature map to identify where scattering would appear. We need Fresnel for reflectance control. And we need a diffuse profile, which will be explained later on. Let's start with the blur. The easiest way to do a blur is to do a box blur, where we will offset the image's UV in all directions and return the numeric average of all the offsets. Here are the sample codes for a box blur function. Remember, we built our shader on top of the standard Cocos PBR shader, so a lot of the groundwork is already done for us. Here, VUV is the uniform passed down from vertex shader containing UV data. We multiplied our scalar parameter by 0.01 because we want smaller values so that our offset isn't too exaggerated. sRGB to linear is a built-in method of Cocos effects that converts sRGB data into linear color space. Remember, color calculation is required to be conducted in linear color space by PBR standards. You're probably going to find that one-time numeric average is insufficient to produce a satisfactory result. You can also run a quick loop to execute the blur multiple times to get a much compelling blur. Box blur is very simple to code, but it is not exactly pleasing to the eye. In computer graphics, we usually use Gaussian blur to process images. The logic behind Gaussian blur is very simple, following the same logic as box blur, but as our offset increases, multiplied by a smaller value weight. The idea is that pixels further away from their original position would be blurred more, whereas the ones near the original position will be blurred less. The weight values should also follow a normal distribution curve so that our blur result would have a natural falloff. Here are the codes after some modifications. The weight values we declared here are arbitrary and feel free to replace with your own. You can find many online generators that generate normal distribution values for you. Let's revisit the red color belt we observed from photos earlier. You might be expecting this color to be a constant color. This is unfortunately not the case. In this example, we have a sphere scattering the red color. We have a fixed light source, and we will gradually reduce the size of the sphere to observe any changes. What we can see is that the scattering color will shift as the size of the sphere goes down. It seems to be following a bell curve, as it started as a dark orange color. Gradually, it becomes brighter. At a certain point, it reaches its peak vibrant color, and then it gradually goes darker again. What we can learn from this test is that scattering color seems to be related to two factors: the distance the light travels and the surface curvature of the material. This is all good to know, but how does it help us with our skin shader? We already have existing data that measures from physical world the exact scattering color and relative scale of the human skin. With this, we can see that the red scattering color on the human skin is actually the combination of light being scattered at different layers of the skin, each with a different scattering color. Also, much like the Gaussian blur we discussed earlier, scattering value follows a normal distribution curve, which is the natural valve we see here. This chart has given us the variance value for the curves at each layer, and with that, we will be able to calculate the scattering value by using the normal distribution function. Speaking of which, here is the function. Now to normalize this, the value for mu should be 0, and the value for 2 sigma square has been provided for us. So basically the function is simplified into something like this. With that out of the way, we can easily come up with a function that returns the scattering color of the human skin for us. Here the parameter is the distance the light travels. Now that we have tackled with the issue of diffuse and scattering color, we still have two more problems to solve. The first one is how to implement the scattering color. Where does it sit in our current render pipeline? The second one is where should the scattering color appear on the face? Keep in mind that we also want this to respond to the different directions the light source might have. Now, Cocos Creator uses the standard metal roughness PBR workflow and unfortunately doesn't offer a translucency channel. Now, this is not going to be a problem because we can easily simulate the effect by using the emission channel. Let's first get our dot products in order. Here, VNormal is the normal data in world space passed down from vertex shader, which is already done for us by the Cocos standard PBR shader. CC Mat View is the built-in parameter for view matrix, and CC Main Lit DIR is the parameter that returns the world space direction of the light source. You can find more on these built-in parameters in the link below. Now let's talk about the two maps we're working on, thickness and curvature. You're probably very familiar with these terms if you are a 3D artist, particularly a character artist. We don't have to worry about calculating these maps in the engine, it would be too expensive anyway. This is because we can easily offline render these maps using an external application. Here are the maps that I'm using. They are baked in Substance Painter. So how are we going to play with these maps? With thickness, the first thing you want to do is to blur it with our Gaussian blur function. I kept the blur amount parameter low because unlike with the diffuse map, I don't want to see any potential artifacts that could be created by the blur in my thickness map. The next thing I want to do is to subtract the blur thickness map by the original thickness map so that we get the delta value in depths. And here is the result. Curiously, if you recall when we take a reference from photos, these are exactly the areas where scattering color is most likely to take place. Now that everything is ready, it's time to put everything together. We have our diffuse profile function that is going to give us the scattering color and its value. But the question is, what should we use as its parameter? V position is the vertex position data, again already done by the PBR standard shader. We're using it as the parameter for our diffuse profile function so that we will have different scattering colors on different depths of the face. We know that curvature is related to the diffuse profile function, but we're not sure of the exact algorithm to use it as a parameter. We do know that scattering fluctuates in a more or less linear fashion as curvature increases. Therefore, we can simply treat curvature as just any other numeric scalar. The combination of thickness map and curvature map will be where our scattering cutter should take place. They will also be controlled by our normal and light direction dot product, so that it will also respond to different light directions. We will add the scattering passes to our emission channel so that we will get the illumination effect that we're looking for. The roughness channel is controlled by the uniform S dot roughness in the fragment shader. With the dot product we prepared earlier, we can introduce more or less roughness to the center or edges of our view angle, hence creating a Fresnel effect. Thank you for joining me in this journey in creating subsurface scattering shader here in Cocos Creator. Hope this video has been helpful and informative, and I look forward to seeing beautiful and exciting projects of your own.